Hello everyone, welcome back to my channel Physics for AP. So today we are going to discuss an interesting and a new topic, which is the carbon and its compound. So we call it as organic chemistry. So when if we divide the chemistry into two equal parts, that is, one is said to be called as organic chemistry and other one is said to be called as inorganic chemistry. So in organic chemistry we will learn only about the carbon compounds. That is what we are going to discuss about today. So that is, we are going to discuss about carbon and its compound, which we call it as organic chemistry. So the remaining, the all the elements, the learning of all the elements like nitrogen, phosphorus, sulfur, the remaining all elements are said to be called as inorganic chemistry. So here we are going to discuss about the organic chemistry, which deals only with the carbon and its compound. So in our episode, so we will discuss about this is about the flow chart, about the whole topic which we are going to discuss is, that is, the first we will be discussing about the physical properties of the carbon, and next we will discuss about the versatile nature. So why carbon is so much of important, that we will discuss in that versatile nature. We will discuss about the hybridization, the first thing, and the second we will discuss about the allotropy, which is a property of a carbon, which in that we will discuss about amorphous and crystalline. And next we will discuss about the catenation, which is called the linking system or the chain system. And next is called the bonds, that is the single bond and double bond and triple bond. So carbon can perform single, double and triple bond, so that we will be discussing. And next we will discuss about the hydrocarbons. In that we will discuss about the saturated and unsaturated hydrocarbons. So types of hydrocarbons will be discussed. And next we will be discussing about the functional groups. So in that we will discuss about the homologous series of the compounds, the carbon compounds, and also we will discuss about the isomerism. And next we will discuss about the nomenclature, that is IUPAC, how to give the names to the carbon compounds and how to draw the structure for the given carbon compound with the help of IUPAC, International Union for Pure and Applied Chemistry. And next we will discuss about the chemical properties, that is the reactions. In that we will discuss about the preparation of alcohol, ester and acetic acid and its various properties. And we'll discuss about the combustion reaction, oxidation reaction, addition reaction and substitution reaction, the four types of chemical reactions. And last we will be going for the chemical reactions by making them as soap and detergents. So how soap and detergents have been prepared and what is the cleaning action of the soap. So that is what we are going to discuss in our carbon and its compound, the total complete episode, the chapter. So first we will go for the physical properties. So when we discuss about the physical properties, so the very first thing that we remember is the carbon having the atomic number as 6, and when we write the electronic configuration we write it as 1s2, 2s2 and 2p2. So in the first orbit we have 2 electrons, in the second orbit we have 4 electrons, that is, as the outermost orbit is having 4 electrons, it belongs to 4th A group, or what we call as the 14th group. And as it has two shells, first and second, K shell and L shell, so it belongs to the second period. So the carbon belongs to the 4th A group or the 14th group, and it belongs to the second period. And let us see what type of bond does carbon form. Does it form an ionic bond or does it form a covalent bond? So as we see, as if we split into ions like C+4 and C-4, as 4 electrons are there in its outermost orbit. Now to get octet rule, so we have to add 4 electrons. So when we add 4 electrons it becomes 8, that means it becomes C-4. Or otherwise if you remove the 4 electrons it becomes the duplet configuration. So when we remove the 4 electrons we get C+4. Now let us see whether these are possible or not. So let us see for cation, that is C+4. So C+4 is nothing but to remove 4 electrons. So when we remove the 4 electrons we get C+4. And as the C+4 is not possible to form. Why? Because it needs huge amount of energy here. So more amount of energy is required, that is the ionization energy. So more amount of energy is required to remove the 4 electrons in its outermost orbit. So as huge amount of energy is required, C+4 cannot be formed. So it is impossible to form as C plus 4. It is possible, but a huge amount of energy has to be given to remove the electron, but it's difficult to remove it. And when we come to the C minus 4, where we add 4 electrons, so when we add 4 electrons, so the total electrons will become as 10 electrons. So as atomic number is 6, we have 6 protons and 6 electrons. When we add 4 electrons, it becomes 10 electrons. Now in the nucleus, the 6 protons we have, the nucleus which has the 6 protons, these 6 protons have difficult to hold the 10 electrons. So here also the C minus 4 is also not possible to form. Why? Because the 6 protons cannot hold the 10 electrons, as it is difficult. So the C minus 4 is unstable, so it cannot form, as well as the C plus 4 is also unstable, it cannot form. Now by this we can know that carbon cannot form ionic bond. So all the carbon compounds cannot form the ionic bond. Now what does it form? It forms the covalent bond. So here the carbon undergoes the sharing of electrons. So when they undergo the sharing of electrons, it forms the covalent bonds. So all the carbon compounds are forming the covalent bonds only. So as example, we know this methane CH4, which has 4 carbons which is been attached, and the CCl4 carbon chloride tetrachloride, the 4 chlorine atoms, and the CH3COH acetic acid, where one carbon can attach 4 bonds like 1, 2, 3 and 4. And here also we have another carbon, so this carbon also can attach 4 bonds, like here 1, 2, here double bond 3, 4, so 4 carbons. So a single carbon can attach 4 bonds around them by the sharing of electrons, which we form it as a covalent bond. So this is about the physical properties. And also carbon, based upon its few properties, it can conduct electricity and it cannot conduct electricity. So based upon few properties, so carbon has a property of a metal and a non-metal. So we cannot say carbon is a non-metal, so carbon is a metal. So due to some of the properties, we can say it's different, as that we will be discussing later. So we have discussed about the physical properties. Next we are going for the versatile nature. So versatile nature is why carbon is said so much of important. Why so much of importance is given to the carbon? That is what we call the versatile nature. So we have different reasons here. In that, first we will go to discuss about the hybridization. So as we have discussed the hybridization in chemical bonding chapter, and let us see here, the carbon can perform sp3 hybridization, sp2 hybridization, as well as sp hybridization. So it can perform 3 types of hybridization here mainly, and it can also perform different hybridizations like sp3d, that all. So let us take an example of these 3, like sp3, sp2 and sp hybridization. So carbon electronic configuration 1s2, 2s2, 2p2, which is in the ground state. So this is the ground state electronic configuration. Now when when an electron which is present in the s orbital jumps to the p orbital, that is when it moves to the excited state, then it becomes 2s1, 2px1, 2py1, 2pz1. Now when these 4, that is 1s orbital and 3p orbitals, px, py, pz, overcome together, that when they intermix together, we get the sp3 hybridization, and as 1s 3p are there, so we get an sp3 hybridization. So example is CH4, and this example we have discussed in our chemical bonding chapter. So here the bond which is formed is sigma bond. All are the sigma bond, the strong bonds are here. Sigma sp3 bond, S is being formed over here. And then coming to the sp2 hybridization, so here we have the electronic configuration as 2s1, 2px1, 2py1 and 2pz1. So 2pz1 has been written separately over here. Why? Because so here in sp2 hybridization, 1 s orbital and 2 p orbitals has to overlap each other, that is they have to intermix each other. Now here what about the 2pz? So 2pz also participate in the bond formation, but they undergoes the lateral overlapping. So as they undergoes lateral overlapping, it forms a pi system. that is the pi bond. So let us say over here as 1s and 2p orbital, when it combines, so it becomes a structure of sp2 hybridization. So this is the structure of sp2 hybridization for one carbon atom. This is for one carbon atom, and this is another carbon atom. So they undergo between them to form sigma sp2 bond, sigma sp2. So this is sp2 hybridization carbon compound, and this is sp2 hybridization carbon compound, like here, which we see in the simpler structure. So here, which the bond which is formed between these two is the sigma bond, that is this is the sigma bond. And here the bond which is been laterally overlapping, the lateral overlapping over here, which is the pi system, we call as the pi bonds, pi pz pz. So the bond which is undergoing over here, which is the pi bond over here, and the remaining bonds which are here, the CH4, C2H4. So here one hydrogen atom and here one hydrogen atom, 3 and 4. Here we get the hybrid bond of sigma sp2 bond s hybridization, as well as here also we get sigma sp2 bond s hybridization. So here in C2H4, which we call as ethene, so which we call it as ethene, so this is called as methane, and this we call it as ethene. So this we call it as ethene. So in this ethene, it undergoes sp hybridization with a double bond of carbon carbon. For one carbon to another carbon, we get a double bond over here. Now if you see for one carbon system, like for one carbon system, as carbon can hold 4 bonds, 1, 2, 3 and 4. So in this, one carbon is combined with 1, 2, 3 sigma bonds and one pi bond over here. In this case, 4 are the sigma bonds. In this case, we have 3 sigma bonds and 1 pi bond over here. The same as also on this structure, which we called as the symmetric shape. And this is about the sp2 hybridization. And next, undergoing into the sp hybridization. Here also sp hybridization, as we have discussed it, 2s1, 2px1 and 2py1, 2pz1, these two are being separated as they undergo the pi bond formation, and the s and p bond undergoes with the overlapping each other, that is they go on hybrid overlap with another bond, that is the hydrogen atoms over here. So this is the main structure of the C2H2, which we called as ethine, So here one carbon is been combined with the hydrogen, and here we have a sigma bond, one sigma bond, that is here this is the sigma bond which we are forming here, this is the sigma bond, and this is py and this is pz. So the py of one carbon atom is being combined with another py to form pi py bond, that is pi bond we are forming here, and one pz will be get combined with another pz to form pi pz. So that is in a single carbon, here in C2H2, one carbon can perform 4 bonds. In that 4 bonds, 2 are the sigma bonds and the remaining 2 are the pi bonds over here. So among 4, 2 are the sigma bonds, which are the strong bonds, and the remaining 2 are the pi bonds, which are the weak bonds over here. So this is about the carbon hybridization. So it can go different types of hybridization. So in that a few examples we have discussed about, it can perform sp3 hybridization, sp2 and sp hybridization. So these are the main hybridizations which can form. That in our chapter, in our discussing the carbonates compound, we will be discussing the compounds all which we are discussing will undergo sp3, sp2 and sp hybridization only. So this is what we have discussed, and we have discussed completely about the hybridization. So we have discussed about the physical properties and in versatile nature. We have discussed about the hybridization. And one more thing is about the bonds. The bonds, that is, it can perform single bond, double bond and triple bond. As if you see here, the carbon can undergo single bond with other elements, other atoms, and the same carbon, another carbon, it can perform a double bond with another carbon. So it can perform a double bond over here, which is double bond, and the carbon, it can perform here the triple bond. As if we take for nitrogen, nitrogen can perform triple bond, oxygen can perform double bond, fluorine can perform single bond, but a single carbon atom can perform a single bond, a double bond, and a triple bond. So that is one of the versatile nature of the carbon. It can perform a single bond, a double bond, as well as a triple bond. So that later on we will discuss about, which we call it as alkanes, alkenes, and alkynes, which we will discuss in the functional groups, that we'll discuss in hydrocarbons and the functional groups, where we discuss about the single bond, double bond, triple bond. That is the alkanes, alkenes, alkynes. So as if you see ane, which is single bond, alkane, alkene, which belongs to the double bond, ene, which belongs to the double bond, and alkyne, ine, the name, last name are called as ine, which belongs to the triple bond. So that we will discuss in the next episode. Next video we will be discussing that. So we have discussed about the physical properties, and we have discussed about the versatile nature, and next we will discuss about the allotropy. So what is meant by allotrope? So which is the another property which we can say that the allotropy is a property of an element which exists similar chemical properties. So its chemical properties all are similar, which are made up of carbon compounds only. So which are made up of carbon compounds which are having similar chemical properties, but their physical forms and their physical properties are being different over here. So that property is said to be called as allotropy. So allotropy is nothing but it is a property of an element in which has similar chemical properties. Their chemical properties are same, but the physical properties are different. It's very simple to memorize the definition over here. So allotropy is nothing but it is a property of an element. It has similar chemical properties and it has different physical properties. Now those type of different forms having, that is the elements which are having different physical properties and different forms, are said to be called as allotropes. Now let us see some of the examples of the allotropes. How in carbon, as we have discussed in a flow chart, that the allotropes of the carbon are divided into amorphous and the crystalline, and in this crystalline we have diamond, graphite, BMF, and nanotubes that we'll be discussing now. And next is the catenation. Is that the catenation is nothing but the chain system. So catenation is nothing but the property of an element. So the property of an element, so which has the longest chain system, which has a linking system. So the sulfur, phosphorus, and some other elements also has the property of the catenation, which we call the linking system. But when compared to sulfur and phosphorus, carbon can perform the longest chain system. So carbon is the only element which can perform the catenation property with the longest chain system. So sulfur and phosphorus can also perform catenation, but they cannot perform the longer chain system. But the carbon is the only element which can perform the longest chain system like this. So it can be performed up to 60 carbons or 70 carbons or 80 carbons. So it can perform a single chain system with like this. So that is what we call as the catenation. So catenation is a property of an element which has the linking system. In that, the carbon performs the longest chain system among all the elements. The carbon is the only element which can perform the very longest chain system. That is why it comes under the versatile nature. So why it is much more important that we have discussed it. And so we have discussed about the types of bonds: single bond, double bond, triple bond, and we have discussed about catenation. We have discussed about the hybridization and physical properties. Next, we have discussed about the definition of allotropes. Now we will be seeing about the different types of allotropes of the carbon compounds over here. allotrope of a carbon, it is a property of an element which exists different physical properties but having same chemical properties. So these are the different property allotropes over here. And if you see here the flow chart of a carbon allotrope, the crystalline and amorphous form. So the amorphous form over here we have coal, charcoal, lamp black, the plant charcoal, animal charcoal, wood charcoal, and so these are the different amorphous form of a carbon allotrope, so which is just like a powder form we call it. And coming to crystalline form, we have diamond, graphite, BMF, as we have seen, we will be seeing now. Now let us move on to the first allotrope of carbon, that is diamond. So it is one of the best known allotrope which has the sp3 hybridization. So each and every carbon compound, carbon atom present in the diamond has a very strong attachment with the another carbon atom. So as they are very difficult to break them, so a huge amount of energy is required to break them. So that is why, so it is known as the hardest material till now known. And next, coming to the allotrope carbon, that is graphite. So graphite, as we know, it is used in the pencil, and it is just not like a diamond. So diamond is a non-conductor, but graphite is a conductor, and it is sp2 hybridization. So it has a pi bond between them for one layer to another layer, so it can easily be broken over here. And the graphite, one layer of graphite is said to be called as a graphene, and that graphene is also used as an electric conductor, which is 200 times stronger than the steel and 6 times lighter than it. And also graphene is the best conductor of the electricity. And coming to the another one, the allotrope Buckminster-Fulleren. So this Buckminster-Fulleren was invented by Richard Buckminster, and it is also called as the buckyball. So when the carbon is being vaporized, it is being condensed into the atmosphere of an inert gas. So those are all combined with a buckyball, that is a carbon compounds. So here we have 60 carbon atoms, which are 12 in a pentagonal shape and 20 in hexagonal shape. And these Buckminster-Fulleren are used in the medical fields to target the cancer cells and to resist the bacteria over here, and it is used mainly in the medical fields. So here we have a monolayer of graphene, the multi-layer graphene, carbon nanotube, and buckyball, which we call the BMF. And next is the carbon nanotube, which is another invention which is done in 1991 by Sumio Lejima. And this when we take one sheet of a graphene and when we roll it, so it becomes a nanotube. So it is used in many fields, like it can be used like a graphite, like as it conducts electricity, and it is also used as a molecular wires, and it is used in integrated circuits as a and also it is used as a biomolecule to inject into a single cell. So that means it is used in a physics subject as well as it is used also in a biology part also. So as it can be used as a biomolecule. And next allotrope of a carbon is the soot, which is also known as a black carbon. It is the second leading cause of global warming after the carbon dioxide. So this is when we heat or burn anything, the soot which comes is an allotrope of a carbon. The another carbon, which is lonsdaleite, which is an hexagonal allotrope of a carbon allotrope, just like a diamond. And here we have another allotrope of a carbon, which is coal. So it is a source, sought after energy source. So these are the allotropes of a carbon. So the various physical forms in which an element can exist are called as the allotropes. So till now we have seen, and right now, thank you for your time, and please subscribe the channel, click the like button, give your valuable comment over here. Thank you for viewing the video.